So here we're going to look at some trigonometric identities, which means we're making a statement that is true and it allows us to make substitutions. So what we'll eventually be doing is kind of verifying identities, where we see this kind of big, long expression is equal to something that's much simpler, and we need to prove that. And in proving it, we go through this process of these substitutions using some of these identities and properties of our trigonometric functions to show that they are in fact equal to each other. So some of these identities we've already used before, so like our quotient identities, so the fact that if you see tangent, you can replace that with sine over cosine. If you see cotangent, you can replace that with cosine over sine. The reciprocal identities, for cosecant, that's the same as 1 over sine, and secant is 1 over cosine. So what we'll end up seeing with these trigonometric identities is that maybe we have something messy involving tangent, cosecant, cotangent, and secant. If we make substitutions so that we get everything in terms of sine and cosine, it reduces the number of functions we're working with. Instead of 4 different functions, then we would just be working with 2. And it's 2 functions that have a really nice relationship with each other that comes through in the Pythagorean identity. Now, the Pythagorean identity we talked about very briefly, but is the fact that if you take sine squared plus cosine squared, then that's going to be equal to 1. So we saw this come up a lot when we were kind of solving right triangles. Now, with this identity comes a bunch of different other forms, and you don't need to memorize all of them. In fact, what I'll do when I go through these examples with you is I just always write this one down and then see if I can rearrange it into a form that I want to use. But just as some examples, what we could do is if we take that sine squared x plus cosine squared x, which actually, before I jump into that, this is slightly new notation for us. This sine with the square right there, that's the same thing as sine of x squared. We just put the notation so that the square is right there, just for a little bit shorter notation, but it's the same thing. But it's good to denote it there rather than having to have the parentheses each time, because the issue would come up where if you drop the parentheses, this means something very different. If you see sine of x squared where there's no parentheses, what we would have to assume there is that it's actually doing this, which is a very different operation. So that's where we're writing out this complete quantity sine of x squared, but we can write it with sine squared of x. All right, so with this form here, we can get some different possibilities. Like if I subtracted cosine squared from both sides, we could have this identity where sine squared x is equal to 1 minus cosine squared of x. So what that means is that as we're simplifying our expressions, if I see this 1 minus cosine squared of x, I can make this substitution with sine squared. Similarly, if I subtracted sine squared from both sides, we could have cosine squared x is equal to 1 minus sine squared x. Some other relationships that come up is, let's see, if I subtracted 1 from both sides, sine squared x plus cosine squared x minus 1 is equal to 0. This is an identity itself. And let's say I subtracted sine squared from both sides. So I'd have cosine squared x minus 1 is equal to negative sine squared. So that's a possible substitution. If I subtracted cosine squared from both sides, we'd have sine squared x minus 1 is equal to negative cosine squared. And I think that's about all of them. So where we have this Pythagorean identity, we have these other identities as well that we can make substitutions with. But instead of memorizing these 5 different identities, what I go with is just memorize this one that links really closely with our Pythagorean theorem, and then from there just be able to find these with subtraction and kind of rearranging the values.